Because some people can understand pneumatic circuits a lot easier than electronic ones, the transistor common emitter configuration has been drawn in such a way that it can be considered as an equivalent of the pneumatic air system shown on the bottom right hand side. So starting with the pneumatic one, just to recap, we have a compressor with a pressure serve 100 psi, and this supplies air via a valve to an orifice and then out into the atmosphere. That orifice may be doing some work like spraying or whatever. If you put a pressure meter across the orifice, you're going to measure a differential pressure, which is a function of the opening or shutting of the valve. If the valve is fully shut, there'll be no differential pressure, and if the valve is wide open, then all the compressor pressure will be across the orifice and there'll be maximum airflow. Now, the valve itself is operated by a reduced pressure through a reducing valve that puts a pressure on the diaphragm, say something like 3 to 15 psi, to open and shut the valve. Now consider the same circuit now using the transistor. Here you have a PNP transistor, and the emitter is connected to the positive of a battery, the battery representing the compressor. Say you've got 12 volts on the battery. Now if the transistor is completely shut, there's no current flow, and therefore, as there's no current flow, all the voltage is across the transistor. If, on the other hand, the transistor is now opened and current flows, then there'll be a differential pressure, or in this case potential difference, across the resistor, which will drop some voltage, and the rest being across the transistor. The base of the transistor is the equivalent of the diaphragm, and onto that we've put a bias which is coming from a variable resistor that takes the job of the reducing valve. Now, using the base therefore to forward bias the emitter base diode, we can open or shut that particular valve. Now, by opening it so that we have some standard level so as to be able to pass both positive and negative, we then apply a signal, a sine wave, through a capacitor to that base, and that then modulates the base up and down. In doing so, the current that goes through is also modulated up and down, and a very small current on the base causes a big current change through the device. Now, the transistor itself is really a current amplifier, and this is shown by the two diodes back to back. The bottom diode is the forward biased base emitter diode, and the current from the emitter, being 100%, is distributed to something like 2% to the base and 98% to the collector. So you can say in effect that the emitter current really goes through to the collector, provided the base has opened it to flow through. And therefore the current goes through the load resistor and drops the voltage across it. Now, the material used for P and N can be obtained by taking a germanium or silicon crystal, where the outer shell is made up of 4 electrons for stability, and by impregnating it with some impurity. The impurity may have less than 4 electrons, say 3 in this particular case for the P, and a hole will be created because we need 4 to complete the crystal. And this hole now can move from one atom to the other, giving us conventional current flow. Likewise, if we have N material, we impregnate the main crystal with an impurity that has 5 electrons, 4 being needed to satisfy the crystal structure, and the extra one being the loose cannon that will flow from one atom to the other as electron flow. Now, taking the P and N together, we have a diode, and even without any voltage across it, at the junction of that diode initially, there's going to be electrons going across to the other side, to the holes, and some holes go over to the electrons. In doing that, when the electrons go over, they leave behind them a positive charge, and when the holes go over to the electrons, they leave behind a negative charge, this being a reverse voltage, a reverse charge, and this now creates a sort of barrier that has to be overcome. And this you can see very well on the graph, you can see on the graph that initially when you start up the voltage there's no current because you haven't overcome this barrier, and then at the break point you've reached the barrier and you've exceeded it, so now a slight change in voltage causes a big change in current, and that is how you're going to get your current amplification through the device. Now the way the transistor works is that the P material that comes up to the base is very thin, so it doesn't take many to satisfy the electrons in the base, which is N material. The rest of them, of course, jump over to the other side and are then collected by the negative potential of the battery. A field effect transistor is a much better equivalent of the pneumatic circuit, because in this case the gate acts very much like the diaphragm in that there is no flow between source and gate. It's a field effect that works here. What you have here is a negative chunk of material which goes from source to drain, and a voltage such that on the drain you have a positive potential which draws the electrons through it. On the gate, if you now apply a negative potential, then this negative potential will cause a narrowing of the channel, because negative will repel negative from the electrons and will end up closing up the channel. So by varying therefore the negative potential on the gate, we can get more or less current flow from source to drain, and again applying a signal we can get the output to be magnified and at the inverse polarity. The big advantage, of course, of the FET is that as there is no current flow at the gate, then this offers a much bigger impedance to very small input signals, and it can therefore be a big advantage at low signal values. The effect of this gate voltage can best be seen here, where you can see on the left hand side a big negative potential which has closed up the channel, and on the right hand side the channel being open to allow a lot of current to flow through.